The overall goal of this procedure is to synthesize superparamagnetic iron oxide nanoparticles and to use those particles to label cells for magnetic targeting and sorting applications. This is accomplished by first synthesizing 10 nanometer diameter magnetite nanoparticles. The second step is to coat the magnetite nanoparticles with a 50 nanometer thick shell of polylactic co-glycolic acid, or PLGA. Next, the magnetic nanoparticles are washed and freeze-dried. The final step is labeling cells with the magnetic nanoparticles for cell targeting and sorting applications. Ultimately, fluorescence microscopy is used to show targeting of magnetic nanoparticle labeled cells within magnetic fields.
The main advantage of this technique over existing methods like antibody-mediated cell targeting is that magnetic cell targeting is highly specific and controllable.
The implications of this technique extend toward therapy for a variety of medical conditions because therapeutic cells can be delivered to the target site while off-target sites are spared.
Generally, individuals new to this method will struggle because careful attention to detail is needed to achieve pure and high-quality nanoparticles.
We wanted to improve targeting and localization of living cells within the body.
Begin by using a Dreschel bottle to degas 500 milliliters of deionized water by gently bubbling nitrogen gas for 30 minutes. To set up the reaction apparatus, place a 500 milliliter 3-neck round-bottom flask within an isomantle heater. Next, cover one side neck with a rubber septum and install a reflux condenser in the other. Continuously run cold water through the condenser. To set up an inert atmosphere for the reaction, first puncture the flask's rubber septum with a needle connected to a nitrogen gas line. Then puncture the condenser septum with a needle connected to a bubbler to visualize gas outflow. Next, install a blade paddle into the center neck with a paddle adapter to maintain constant stirring of the reaction mixture. Attach the blade shaft to an overhead stirrer mounted on a stand. Purge the flask with nitrogen gas and leave nitrogen flowing into the flask at a low but detectable rate. Then remove the reflux condenser and add 1 gram of iron 3 chloride, 612.5 milligrams of iron 2 chloride tetrahydrate, and 50 milliliters of degassed water. Replace the condenser and stir the reaction at 1000 RPM while heating to 50 degrees Celsius. This will produce 10 nanometer diameter magnetite particles. Once the reaction has reached 50 degrees Celsius, use a syringe to inject 10 milliliters of 28% ammonium hydroxide through the flask septum. As the magnetite precipitates, the solution should turn black. Remove the rubber septum and gas line and heat the reaction to 90 degrees Celsius. Then add 1 milliliter of oleic acid to the flask to coat the nanoparticles and form the magnetite gel. Next, replace the septum and the gas line on the flask and remove the condenser. Turn off the heat and stir the reaction at 500 RPM for 2 hours. After stirring, decant the excess liquid while holding the nanoparticles at the bottom of the flask with a strong magnet. To begin purification, first dissolve the magnetite gel in 40 milliliters of hexanes. Slowly pour this solution into a separatory funnel containing 40 milliliters of degassed water and gently swirl the funnel for 5 minutes. After swirling, decant the lower aqueous fraction. Wash the magnetite solution twice more with degassed water in a similar fashion. Next, transfer the magnetite solution to an Erlenmeyer flask. Dry the solution by adding several spatulas worth of sodium sulfate and swirling the mixture. Then vacuum filter the mixture through 1 micrometer filter paper. Set the water bath temperature of a rotary evaporator to 50 degrees Celsius, with 24 degrees Celsius water circulating through the condenser. Then transfer the filtrate to a 50 milliliter evaporating flask and evaporate the hexanes for 2 hours at a moderate rotation speed under vacuum. In glass vials, collect the magnetite gel into 6 40 milligram aliquots. Coating and washing will be done to each aliquot separately. Add 1 aliquot of gel together with 40 milliliters of PLGA in ethyl acetate in a plastic beaker and sonicate the mixture for 10 minutes. Next, add 80 milliliters of chloronic F127 to the beaker and immediately emulsify with a mixer at high setting for 7 minutes. These nanoparticles are now superparamagnetic iron oxide nanoparticles, or SPIONs. Dilute the solution with 1 liter of deionized water and sonicate in a fume hood for an hour. Then place a strong magnet next to the solution and gently stir the solution to collect the spions at the magnet. Decant the aqueous solution while retaining the spions in the beaker. Wash the spions 3 times with water, sonicating each time. After all 6 aliquots have been coated and washed, collect the spions into a single glass vial. Freeze-dry the spion solution overnight in a lyophilizer. To prepare for cell labeling, first suspend spions in PBS at a concentration of 40 mg per milliliter and sonicate them for 30 minutes. Next, add the solution to a flask of nearly confluent cells at a concentration of 5 microliters per milliliter of cell culture medium. Rock the flask to evenly distribute the spions. Incubate the cells for 16 hours at 37 degrees Celsius. Gently aspirate the culture medium, and then wash the cells twice with PBS. The magnetically labeled cells can now be used for experiments. Magnetite nanoparticles with a diameter of 10 nanometers can be consistently made by stirring an aqueous solution of iron 3 chloride and iron 2 chloride tetrahydrate at 50 degrees Celsius and 1000 RPM. Transmission electron microscopy, or TEM, is the preferred method to determine particle size. Coating the magnetite nanoparticles with PLGA using a high-speed emulsifier reproducibly results in PLGA magnetite spions with a diameter of 120 nanometers. Scanning electron microscopy, or SEM, is used to visualize these particles. Incubation of blood outgrowth endothelial cells with spions for 16 hours results in endocytosis of the nanoparticles. Using TEM, the PLGA magnetite nanoparticles can be visualized in the cell, where they are stored within cytoplasmic endosomes. The loading of iron into the cells is high enough to achieve magnetic capture of viable cells to ferromagnetic implantable medical devices. The magnetically labeled endothelial cells are attracted to a ferromagnetic stent at a higher rate than a non-magnetic stent.
While attempting this procedure, it's important to remember to thoroughly wash all glassware and equipment to maximize the purity and safety of the nanoparticles.
Following this procedure, other methods like magnetic cell targeting can be performed in order to answer additional questions like which medical therapies can benefit from specific and controlled delivery of cells.
This magnetic targeting technology shall enable the development of focused cell delivery for a variety of biomedical applications.
After watching this video, you should have a good understanding of how to synthesize superparamagnetic iron oxide nanoparticles and use those particles to label cells for magnetic targeting applications.